I'm going to record now. All right, guys. Hello. Today, I think I will do a lecture, just like I said in the email, because you know there's so much things to cover. That's the never-ending story in number theory. Unfortunately, I cannot cover an entire one-semester number theory course in just 1 week or 2 weeks. So that's why I decided to do a lecture now. And then afterwards, I will do a recitation by my own, probably tomorrow, depends. I'll solve some problems. Okay, so today, let me get started. Today, we're gonna talk about, well, like I said, I have to select some topics for me to talk about. And then I decided, I looked at some of the Putnam problems, and then I decided to talk about the Diophantine equations and some analytic methods in number theory. You will see a little bit of analysis today. Well, I hopefully not too much, but I will try to stick to mostly to that analysis which is relevant to number theory, especially to prime numbers and whatever. But now I would like to start with some Diophantine equations. So the first part. About Diophantine equations. Okay, and here, well, you know, there are a bunch of methods on how to solve Diophantine equations, but there are plenty of them. For example, you know, there's this Pythagorean equation. For example, which says that the equation, so it's x squared plus y squared equals z squared, has infinitely many solutions. In Z, right? And there are plenty of other equations, like I said, and methods to study these. And I'll leave this to you as a research, as an exercise to figure it out how you can write the solutions to these infinitely many solutions. You can actually write them in terms of of a parameter. And I'll leave it to you as an exercise. And now I'd like to start with some easy examples of equations. And there will be a bunch of methods, so I'm just gonna stick to some simple methods. So methods for solving Diophantine equations. Okay, and the first method that I have in mind is, let's say, the bounding method. If I can call it like this. Well, the bounding method says the following. Basically, I have an equation, and then I derive some inequalities, which will help me to reduce the cases. For example, a good problem is the following. This was some kind of a Russian Olympiad. I don't know which year, which says the following. It says that find all positive integers. Let's say x, y, such that we have the following. X cubed minus y cubed is xy plus 61, right? So this is what we call a Diophantine equation. As you can see, I have these two variables, x and y, and I need to find them such that they satisfy this. Well, when you see this kind of equations, well, try to think of some, what I would say, some rudimentary methods, like try to think as simple as possible. Well, what would you do in this case when you look at it? Does this ring a bell to you when you look at this equation? So do you see any formula? Does this, for example, this guy here, x cubed minus y cubed, does this ring a bell to you? Well, what do you know about it? Oh my. You know that x cubed minus y cubed is x minus y times x squared plus xy plus y squared, right? So, and we know that, so we have that. So the equation reduces to what? To x minus y times x squared plus xy plus y squared equals xy plus 61. So now maybe we should do something about it. So what do you think we should do here? So the question is, can we derive an inequality for this guy? For example, for for this guy here, do you know any? Do you remember from the first, we talked about it? So now maybe I should, okay, let me assume that. So first, let's notice that x is greater than y. Because otherwise, we'll have a problem, right? So therefore, we have to consider what do we have to consider? So we have to consider that x squared plus xy plus y squared is less or equal than xy plus 61, right? Or x squared plus y squared is less or equal than 61. So this is how we bound this equation. So we try to think of some inequalities. Okay, so we have this. And now since x is greater than y, it follows that, so it will follow that, that what? That 61 will be greater or equal than x squared plus y squared, which is greater than, since I know that x is greater than y, this will be, okay, let's say greater or equal than 2y squared. So from here, I have only a few options for, so it will follow that 61 over 2 is greater or equal than y squared. So what options do we have for y? So y will be what? So let's see, 61, 60 over 2 is 30, square root of 30. So it will be close to 25 is the largest square, right? So we will have 1, 2, 3, 4, and 5. So these are the options. These are the options for y. Okay, so since I got this now, then only finite number of cases, then, well, I'm in a perfect situation. And now I want to see what happens for each one of them. So now we take for y equals 1, what do we get? What equation do we get? We get x cubed minus x, let's see, minus x plus minus 62 equals 0, right? And I'll leave this to you as an exercise, and we keep going. Y equals 2, we'll get what? We'll get x cubed minus 2x minus 69, minus 69 equals 0, right? And so on. And we keep going. I think I've done it here. For y equals 5, we will get what? We will get something like x cubed minus 5x minus 186. This guy is 0. And now you will solve each of these equations, each one of them. And then you will see that the only solution, so solving, and I'll leave this to you as an exercise, solving each equation will give us that the only solutions we have are 6 and 5. Okay, so that's how we solve this by using inequalities.
I have a question.
Yes.
Why did you choose 2y squared and not just y squared? Why did you choose the coefficient to be 2 for that inequality?
Here? Because x is greater
than or equal
x
to
is greater than y, right?
Yeah.
So x squared plus y squared will be greater than 2y squared.
Okay, but why not just y squared? I mean, why did you choose 2y?
Because you wanted to well, okay, I see what you mean. So you are asking, you want to neglect this just to be greater than 0, right?
Yeah, because we know x is greater than y, right?
Yeah, it's greater than y. It's good for me to have 2y, y to be as large as possible, because if you have only y squared, you'll have more cases to check.
Okay.
So
because you divide 61 by 2, right? And so you have,
yeah, exactly. So it's as small as possible. So I want us, I don't want to check too many cases. I want y to be as small as possible.
So could you have chosen like a coefficient greater than 2 and have even fewer cases?
Yeah, you could have chosen, you could have neglected just this guy, x squared, right?
Yeah.
And then you could have said something like, okay, let me neglect this. So this is greater than 0. This is greater than y squared, but y squared will be less than 61. So 61 will be, you'll have more. You'll have 5, 6, maybe 7.
Right.
So you don't want to do that.
Okay.
Right? So that's why you're trying to check as few cases as possible.
Gotcha.
Anyway, so that's the first example. Now, I would like to say maybe to use some modular arithmetic. So this is the bounding method. Now let's see, how should I say it? Modular arithmetic method. And in this case, you'll see that we'll try to see what happens with this when we mod out some number. And the example that I have in mind, so problem 2, is the following, and then I'll do a Putnam problem. Let me think. In fact, since we're talking about that problem would be from 2001, why not? So find all integers. Let's say xy, such that x squared minus y factorial is 2001, let's say. And now we would like to see what happens here when you look at it. You see that you have this number 2001, which is a bit large. And you have also the factorial, so which is large again. So maybe you should do something. Maybe you should mod something so that you can make things easier. And usually when you mod something, you try to mod a prime number. So we consider, let's say, let's see what happens. So we want to see what happens modulo 7, let's say. Right? Now let's see, modulo 7, what's going on with this. And now I want to look at it. And I want to look at this equation. I think somebody has his mic on. I think it's Caroline or Gabriel, one of you guys. I think. All right, so mod 7, I want to see what happens mod 7. So when, let's say, y is greater or equal than 7, right? We know what? We know that y factorial will be congruent with 0 mod 7. Right? That's obvious because the factorial will consist of the number 7 there, right? Y factorial will be 7 times 8 times all the way for y greater or equal than 7, right? That's obvious. So what does this mean for our equation? So this means that since y squared is y factorial plus 2001, this means that what? That x squared will be congruent with what? Can you tell me? With 2001, right? Which this guy, 2001, will be congruent with -1 mod 7. Okay? Right? Keep in mind that y squared is x squared plus 2001. And we know that y squared is 0 mod 7. So clearly it follows x squared is congruent with 2001, which is -1 mod 7. Okay, great. So this means what? So I know at this point that x squared is 1 mod 7. So if there, so this means, so if there is an integer, how should I phrase it? So it follows that there is an integer, let's say x, so integer x, no, maybe I should know, I mean, that's not, okay, let me rephrase it. So if there is an integer, x, right? Then which satisfies let's say this equation, the above equation, then clearly this guy x will be x squared is, then x squared is, well, is 6 mod 7, right? And now let's analyze everything. So now let's analyze the solution of our equation. Okay, and now let's see. So we're going to draw the following chart. So I have x, then I have x squared mod 7. I want to see what's going on. And now for x, I'm taking all these values, 0, 1, 2, 3, 4, 5, 6. For each one of them. All right, let's see. All right. Now, what can you tell me? When x is 0, x squared mod 7 will be 0, right? That's obvious. when x equals 1, x1 mod x squared mod 7, right? We've done this, so it's 1. When x equals 2, x squared mod 7 will be 4, so no problem. When x equals 3, x squared mod 7 will be what? So what is x squared mod 7? When x equals 3. So x equals 3, x squared is 9, right? 9 mod 7 is what?
12, right?
2, right? When x equals 4, what do you have? X, so you have
2 again.
2 again. For 5, what do we have? So 25. 25 more mod 7 is what?
5.
No.
Or no. It's 4.
4. And when x equals 6, 36 mod 7 is what?
1.
1.
Yeah.
Correct. All right, so I have this. So what does this mean? As you can see, all this, it will imply that, so for, you see, do you see any 6 there?
No.
Not quite. So this is what happens. So I looked at the case when y is greater than some number, and I've done, and everything I have obtained, it's a contradiction, right? So, and where this, I looked at this guy when this guy is greater or equal than 7. And now, well, you see, I don't see any 6 here, so x squared cannot be congruent with the 6 mod 7, or negative 1 mod 7, as you can see. I only have these values, so therefore, this implies that y is less than 7. Usually this is how you study these kind of equations. Okay, and now for y, well, not less than 7 factorial, so I want to make myself clear here. It's a 7 exclamation point, but anyway, I don't want to confuse you. So y is less than 7, strictly less than 7. And what do we know? We know that, y, now we can check the cases. Oh my goodness. So we must check the cases. So and we have to see which one is a check some cases. And now let's be careful here. So let's write the equation again. So the equation was x squared. So I know that x squared equals y factorial plus 2001. So for the equation, for my equation. And keep in mind now that I have this. So y squared will be, let's see, so 7 factorial is what? Well,
Well, we don't need to do 7, right?
So it will be a little bit too, so I know why. So at this point, you know, I have finitely many solutions for this equation. So I have to put my hands on some of them and to see which one works, which one doesn't work. So that is the thing I have. This is what I have to do, right? So let's see. So what is the smallest perfect square greater? So the question I want to ask you is, what is the smallest perfect square? Let's say, yeah, greater than 2001. So let's look at this. Which one is it?
45 times 45, which is 2025.
Exactly. So it's The answer is 45 squared, which is 2025. So that is the nearest. So now let's look at it. So the nearest perfect square. So what kind of solutions do we have here?
It would have to be y factorial is 24, which is,
Wouldn't y have to be 4 factorial?
yeah,
4 times 3
Well, which is 4 factorial is what?
is 24 plus 2001, which is 2025.
Yes, and you will take what? The square root of that, right?
Yep.
So this will give us, but also the square root of 2025, it's also negative 45 squared will give us 2025, right? So this gives us two solutions, which will be what?
45.
And 4,
yeah.
right?
Yeah.
So this will be 45 and 4, and negative 45 and 4. Right? Okay. So now this will cover all the cases for, so this covers all cases for which y is less or equal than 4. And now, well, not 4 factorial, again, it's 4. And now let's see what happens for 5 and 6. Well, for cases y equals 5 and y equals 6, I'll leave it to you as a homework to see why these do not have any solutions. An exercise for you, homework. You will see that for y equals 5, there is something going on there. It will give us that x squared is 2001 plus, what is it? 5 factorial is what?
It's 120. So
120.
2121.
Exactly, 2000, yeah, 2121, right? Then you will see why this is not true. Okay, so the only solutions, so we don't have any solutions. Okay, no solutions. So the only solutions are this guys here. And you can check them by hand. They actually verify the equation. So the only solutions are xy, are those above, 45 and 4, and negative 45 and 4. And that's it. Okay, so this is how we use modular arithmetic, because you can see there are plenty of other examples. You know, I could have, maybe I should give you one. You know what? Yeah, maybe I should give you one. So another problem number 3. And maybe I will just discuss this briefly. I will just give you the idea. So basically it says that find all solutions to the equation. Let's say x to the 5th minus y to the 4th equals 4. Minus y squared, let's say. That's a little bit too much. Y squared equals 4. Right? And so in positive integers. And as you can see here, when you look at this equation, you have to look modulo of prime. So the same idea. So, okay, let me give you the solution. Only the main idea I'll give you. So the main idea for this equation is to work modulo a prime. And in this case, you will see, and I'll leave it to you to figure out why we'll work modulo 11. And then you do the same thing. Well, what is the motivation behind working modulo 11? Well, so the motivation is the following. So this is a way to look for why you should look modulo 5, 7, or 11. But in this case, when you look modulo 5, you see you won't go anywhere. When you look modulo 7, the same thing, but modulo 11 will give you something. And this is what happens. The motivation is that when the JCD, the greatest common divisor between x and 11 is 1, right? These are relatively prime, x and 11. We have that, and this is a nice observation. We have that x to the 10th is congruent with 1 mod 11. Why is this true? Can you tell me? What is this? This is an application of what? You remember Fermat's little theorem? What does it say? That I have a number a to the p minus 1, in this case is 11, is congruent with 1 mod p. Do you remember that? If the JCD between a and p is 1, right? So that's the motivation behind this. And then when this happens, then when x and 11 are relatively prime, when the JCD between x and 11 is 1, then you can do a trick here, a magic trick. Then we have that, we can write that x to the 5th, and you square this guy, right? So, well, this is congruent with 1 mod 11. Anyway, and now you can substitute, right, y to be x to the 5th, and then you see what happens mod 11, and then you write that y squared is congruent with 1 mod 11, and you keep going, so etc. I'll leave it to you. So I'll leave it to you as an exercise to continue this problem. It's a very nice problem. And then you'll end up at some point with some cases, and then you'll draw a chart to see what happens with x. And you take all these numbers, it's mod 11 from 0 to 10, and then you'll see with x squared, with x to the 5th what happens, and then to y squared what happens. And you will see that they do not agree. So when you draw the chart for x to the 5th mod 11 and for y squared mod 11, you will see that they do not agree. So the equation does not have any solution. So you'll get that the equation does not have any solutions. Anyway, does it make sense what I'm saying? So that's the main idea. This is a very nice trick. So try to, but now to finish, but now I want to do something. There is another problem. I don't want to lose too much time because I want to do some, anyway, problem number 4. And I would like, in fact, I would like to do this together. And this problem is a Putnam, I think it was a Putnam A5 in 2001. So the problem says the following: prove that there are unique positive integers a and n such that a to the power n plus 1 minus a plus 1 to the power n is 2001. So again, with this number 2001. So let me, again, let me show you the main ideas. So first of all, I'd like to ask you something. Can you tell me something about this number 2001? Is this a product of some prime numbers? What do you think? Because this will be important. So if you multiply, let's say, is this a product of a prime numbers? That is the question. And what are those numbers? Because you'll see that this will be important when we mod something out here. Well, so that's the main idea. So how would you write 2001? But then, okay, you'll answer this to me. But before that, what if I mod out? Let's look at the equation. Just let's look at it very, very carefully. When you mod A, for example, so if we take modulo A, so taking this equation, the given equation, modulo A, mod A. So what do we have? We have what? Well, mod A, that guy will just vanish, a to the power n plus 1. So a to the power n, whatever, all this with a will vanish. But we have this 1. So it will imply what? It will imply that a is divides 2001 plus 1, the last term, which is 2002. So taking mod out, it's we have this, taking mod A. So this is the first step. But now, maybe in this decomposition of 2001, maybe you'll have a 3 there. Did you guys figure it out? How can I write 2001 as the product of some numbers, of some prime numbers? How can I write it? What are the prime factors of 2001?
3, 23, and 29.
3, 23, and 29. Let's keep this in mind. All right. Maybe I'll do something, mod something. Maybe. So now since I have that 3 over there, maybe I should mod 3. Look at this equation, mod 3, to see what's going on. So now taking mod 3, what do we have? So mod 3, what do we have? So I know that 3 will divide. So we have, so 3 divides 2001. So we have that a to the power n plus 1 is congruent with a plus 1, everything to the power n, right? Mod 3. Okay, that's good to know. So mod 3, these two are equal. So what does this imply? So if you look at this, this implies that so this implies that A is congruent with 1 mod 3. So this is what we're going to get. All right. So once we have this, it will follow that what? That, and it follows that n must be even. N is even. Okay, that's a good, that's a very important piece of information. So we know that n is even. And now, well, we have two options for A. So now you can analyze if A is even, will you see what happens? So now when A is even and A is odd, so when A is even, so what do you know? When A is even, it follows that A to the power n plus 1 is what? Well, n is greater than 1, a squared, so it will be at least 0 mod 4, right? So and now you'll see that okay, no, let me put it like this, because if A is even, so if A is even, then we have this. And then at some point you will obtain a contradiction. So this implies that, so what do we have? So A 0 mod, so A plus 1. So this will imply that, so anyway, so we get a contradiction. You can figure it out. Get a contradiction. Okay, so this implies that A is odd. Okay, and when A is odd, you have several possibilities for A. For example, we have, what possibilities do we have? So we can have something like, anyway, I'll leave it to you. So we can have like 7, 13, and 91. And then you'll just study them. You'll see a modulo, some numbers, what happens, and so on. And then you will see at the end that you will arrive, so there is only one solution. So at the end, the only solution for this equation is 13, and so A is 13 and N is 2. So that's it. Anyway, I'll leave the details to you. All right, since I don't want to lose too much time, like I said, I want to cover something else, and I'm already behind of it. So in a nutshell, this is how what you should expect from equations. Well, there are plenty of other methods, but I think these are the most basic methods that you will encounter. And now, well, let me start with the second part. Let me see here how so the second part is some analytic methods. In number theory. And here I would like to dwell more on prime numbers. Okay. Well, you know, so these are the prime numbers, you know, 2, 3, 5, 7, 11, and so on. These are the prime numbers. And you know that from Euclid. So Euclid's theorem, in fact, you can actually prove it, that there are infinitely many prime numbers.
Cezar?
Yes?
It's also true that as t goes to infinity, they become more spread out. Like the recurrence of each consecutive prime integer is more spaced out the more you have of them.
You mean the difference of any two consecutive, for example, like
Yeah.
Pn plus 1 minus Pn?
Yeah.
Well, it's a spread out. Actually, well, if you look at the lim sup of this, right, the largest margin of this, actually it's bounded. It was proven. It was recently, it was a conjecture, like, what was, let me see. It was proven, actually, it was a big result.
It's like an approximation, right?
It's actually deeper than that. Let me see. Yeah, about the distribution of primes. Wait, let me. Wait. Yeah, the bounded prime gap, bounded, yes. So yeah, actually it was the lim inf. All right, let me mention it. So there is this result of Yitang Zhang. I think it was in 2014. So this theorem. Since you brought it up, 2014, right? Which says the following: prove that lim inf of this guy is actually bounded. It's less than 7 times 10 to the 7. And in fact, this was actually improved, this constant, by some mathematicians. They reduced it to 246 or something like this. These are very, very deep results.
So you say it's bounded, right? But there are infinitely many prime numbers, right?
Yeah. But the difference of any two consecutive, right? It's at some point this limit is going to be bounded. Yeah, this is actually a very deep result. Like,
so what you're saying essentially is that the difference between any two very large prime numbers is going to approximate, be less than that value, more or less.
Yes. For example, take, I don't know, try to cook for some very large values, like some billions, and you will see that the difference of these two will be less than that value. That was a huge result. Still, it's a huge result in mathematics. And also, the twin prime conjecture basically says that it is conjecture that this guy is actually 2. But that's the conjecture. So as you can see how far this is. And in fact, this was proven by earlier result, again published in the Annals of Mathematics, that this difference is this prime gap is less than infinity, but it's finite, it's bounded. That's what they proved. But Yitang Zhang actually proved that. Look, I can look at this guy here.
Basically, large primes are going, or the difference between any two large primes are going to cluster around that value.
Yes. Well, even less. Yeah, but no more than that.
Yeah, less.
So like I said, these are very, very deep results. This was actually published in the Annals of Mathematics, like the top 1 journal. So anyway, honestly, I don't, like I said, it's deep mathematics here, like Fields medal type of results. Unfortunately, he was, Fields medal has this, the committee for Fields medal has this absurd rule, I would say, at this point, that you should be below 40, because they say like a mathematician is the most creative, reaches its peak of creativity below 40, which I don't think is not valid these days anymore. So this guy was like 50 and something when he proved this. So there is hope, like things change.
You still got time,
change.
Cezar.
Say that again?
You still got time to get your Fields medal, Cezar.
No, they still have this rule for 40 years. That's why they didn't award this guy a Fields medal, but probably he deserved it for this result, like easily. Anyway, so these are the prime numbers. And in fact, now since I would like to mention, so these are the prime numbers. Let's say P1, P2, Pn. Let's say are prime numbers. And this guy, let's say with Pn is the nth prime number. Okay. And now I'd like to say a few things about this. And but the first thing I would like to say is the Bertrand's postulate. Which says the following, it's very nice. Between n and 2n, there exists a prime number. For example, when you take, let's say, n equals 2, between 2 and 4, you find 3. Let's say n equals 4, between 4 and 8, there is 5, for example. There are actually 2 of them. So between any n and 2n, between, let's say, between 100 and 200, you will find at least one prime number. Well, there are actually more than one, but at least one. So there exists, okay, let me rephrase it so it makes, there exists at least a prime number. And I will rephrase this a bit. So if I denote, if we denote pi of x, which is the sum, so this is the prime counting function. And actually I talked about this yesterday's talk at the math club. So this is the prime counting function. Then the Bertrand postulate, Bertrand's postulate can be written as pi of 2n minus pi of n is greater or equal than 1. So this is how we can write the Bertrand's postulate, right? So pi of x is the prime counting function. Look at it the way it's defined here, right? So given a real number x, I'm counting how many prime numbers are less or equal than that number, x. Okay, so this is Bertrand's postulate, but so we have something asymptotically. Unfortunately, this, you see, this prime counting function does not behave like other arithmetic functions, right? In fact, it's not even an arithmetic function, this, multiplicative, whatever. We don't even know if this function is additive. We don't, in fact, there is a conjecture of Littlewood which says that the prime counting function is sub-additive, whatever that means. Anyway, in fact, I think I discussed this with Jack about this. And I suspect that, well, this is just my hunch, that would be equivalent to the Riemann hypothesis, but whatever. That Hardy-Littlewood conjecture. Anyway, I don't want to get into this, so let's stick to our purpose. And now I'd like to give you something very strong, prime number theorem. Which says that there is an estimate, an asymptotic estimate for the prime counting function. In other words, it says that pi of x is asymptotically equivalent with x over log x as x approaches infinity, or equivalently, we can write this. So this means that the limit as x approaches infinity of pi of x over log x. By the way, log x here, log x here, it's a natural log. This limit is 1. And as an immediate consequence, and I don't want to prove this, so as an immediate consequence, we have that it follows that if that Pn is in fact equivalent with n log n as n approaches infinity, right? This Pn is the nth prime number. So well, like I said, or if you want, you can write it in this way: the limit as n approaches infinity of Pn over n log n is 1. Again, log n is the natural log, so this is how you can write this. And also this. So this is the prime number theorem. Again, a very deep result. Very, very deep result. Anyway, I don't want to get too much into details, but there is also another theorem that it's important here, which, well, I'd like to make one comment that this prime number theorem was proven for, empirically was observed by Gauss, who actually said that this pi of x behaves some similar, well, asymptotically, is asymptotically equivalent with some logarithmic integral, whatever, and that logarithmic integral is equivalent with x over log x. So, but it wasn't proven by Gauss. It was proven by two French mathematicians, de la Vallée-Pouzin and Jacques Hadamard. These two mathematicians, and then they used complex analysis to prove this. But then in 1934, I think, Atle Selberg and Paul Erdős proved this without, they proved it independently without the use of complex analysis. But anyway, as Selberg was actually awarded the Fields Medal for this. So you see, these are very, very deep results with tremendous consequences. Well, I don't want to mention all of them, but one of them is just this guy here, that asymptotically you can say that Pn is n log n as n approaches infinity. Okay, now there's one theorem that I would like to mention, which we'll call Dirichlet's theorem. Which says the following: if I have two integers, a and b, right? This is, again, a very deep theorem. I'm not going to prove any of this. In fact, all these theorems that I just mentioned, the last three theorems, Bertrand's postulate, prime number theorem, and Dirichlet's theorem, you do them in a graduate course. Jack, did you do this in a graduate course, or it was more algebraically oriented?
It was mainly algebraically oriented.
Algebraic. This is more analytic, okay. Because usually these are the cornerstones of an introduction to analytic number theory. So if I have two integers with relatively prime, then there are infinitely many primes. Of the form a n plus b, right? For any n positive integer, right? This is again a very deep theorem. Well, unfortunately, I'm not going to provide an example of this. And now let's do some problems. Well, I don't know which. Anyway, I'll say problem one. And the problem one that I have in mind, and you'll see how powerful is to use one of these tools, is the following. To show that, and we'll experience this sequence again, that this sequence, the harmonic sequence, 1 plus 1/2 all the way plus 1 over n, is never an integer for n greater or equal than 2. So let's look at it. Well, usually, well, you can prove this by just looking at the exponent of n and so on. But I would like to use one of these tools. And what I'm going to do, we will use what we call Bertrand's postulate. And actually, I like to do this problem this way. Always when I teach number theory, I always like to do this solution. And actually, moreover, this was a Berkeley preliminary exam problem. So for PhD students, this was one of them, I think. I don't recall exactly which year, but this was one of them. So they like to look at all Putnam problems and to put them in a preliminary exams for PhD students. So now let's see, we would like to use, like I said, Bertrand's postulate. Oh my. So now what we're going to do, so Bertrand's postulate, so we can guarantee that there exists a prime number let's say P in the interval. So we know by Bertrand's postulate that is between n and 2n. So we can guarantee that there exists a prime number between n over 2 and n. Right? We can know this. And now we're going to make a choice. So let us consider the largest such prime. Right? And now we can write in the following way. So now we can write Hn as, and now look what I'm going to do. I'm going to write it in this way. So now we write the harmonic sequence in the following way. So I'm going to put on the bottom n factorial, and now I'm going to write it in this way: n factorial over 1 plus n factorial over 2 plus all the way n factorial over n, right? I can do this. So that's the tricky way of writing this. And now clearly, well, clearly P, this this largest prime number in that interval, P divides the denominator and all summands in the numerator. But except one. Okay, except one. And that would be what? N factorial over P, right? Since P is greater than n over 2. And that's it. So Hn cannot be an integer. All right, and that's it. You see how easy this was with using using the prime number theorem. Using Bertrand's postulate. And now I have many other problems which I like to do, but probably I will do some of them. I'll think about it. Some of them I will leave them for the recitation. But before that, I'd like to do one more problem. So problem 2. Probably I'll do 2 recitations, 2 separate recitations as well. So problem 2 says the following: let A and B be integers such that A to the power 2n plus B is a perfect square for all n greater or equal than 1. Show that B is a perfect square. All right, I want to to show you the technique here. So I'm just going to use analysis to solve this problem. And the idea is the following. I want you to pay attention. We will use some kind of a convergence stuff or sequences, but when we'll talk more about analysis, you will see what I mean. Now let me look at this sequence. So let's consider the following sequence. Xn n greater or equal than 1, and xn is the square root of a to the power 2n plus b, right? And now I'm going to do the following trick. Let's look at this guy here. 2xn minus x sub n plus 2. Okay. This guy, if we look at it, this is nothing else than just a times 2 to the power n plus b, 2 minus the square root of a to the power 2n plus 2. Sorry, what am I doing? Yeah, plus b. Or you can write this as the square root. Let's be very careful here. So I'm gonna, so this would be a to the power 2n plus 2, right? Plus 4b minus the square root of a to the power 2n plus 2 plus b. And now, since I have this, the difference of any two radicals here, I can apply the conjugate, and I can write this as, by applying the conjugate, I'll have on the top, what do I have on the top? So here on the bottom, I have a to the power 2n plus 2 plus 4b plus the square root of a times 2n plus 2 plus b. And on the top, what do I have? Can you tell me? When you apply the conjugate. So a times 2 to the 2n plus 2 minus a times 2 to they vanish. So it will be 4b minus b, which will be 3b. Okay, beautiful. Also keep in mind, so let's write here, that since this guy is a perfect square, this sequence belongs to Z. And in fact, it's a positive integer, right? Now, as n approaches infinity, let me write it here. What can you tell me about this guy? This will approach what? This radical here. Can you tell me? This will approach what? As n approaches infinity, this will approach, well, 0, right? This is infinity, so this approaches 0. So the limit as n approaches infinity of 2xn minus xn plus 2 is 0. Yeah, but the difference here is these are sequences of integers. This implies that at some point, since the limit is 0, but this sequences of integers, we have that, actually that difference is 0. 2xn minus xn plus 2 is 0 for all n greater or equal than, let's say, k. So this means that this guy is 0. But when this is 0, when, well, look at it, when this is 0. So it follows that b is 0. So 3b is 0. So b is 0. Well, this follows that, this implies that a times 2 to the n is a perfect square. For all n greater or equal than 1. So this means that what? A, 2a, so 2a, 4, so greater than 0, let's say. A, 4, 2a, 4a, 8a, and so on is a perfect square. This happens only for, so a is 0. So it follows that b is 0. All right, maybe I should have explained it a bit differently. So this means that if sorry, it follows that b is a perfect square. Right, this is what that was the statement. No, b is a perfect square. Okay, maybe I should explain it a bit differently here. You see, I want to, if b is different than 0, then this limit is 0, then that the difference of that sequence is 0. So at some point it follows that b is 0, contradiction. So b must be 0, right? And this means that a times 2 to the n is a perfect square for all n, and then this means that a is 0. So it follows that b is a perfect square. But anyway, you will understand what I mean by that. Okay, I think I'm gonna stop here. Thank you very much. I know it was a bit, I had many other things to cover, but probably I'm gonna do some of the problems in the recitation, and I'm gonna stop here. Thank you very much.